So I introduced Nilesh already earlier. I don't have to do it again. This time he's going to tell us about quantum physical unclonable functions. Welcome.
Yeah, thank you so much. So I have talked with a lot of you, and I guess all of you have heard what is physically unclonable functions, but you don't know the details of it. So in this presentation, what my goal is to introduce physically unclonable functions and give you some review about what is a quantum physically unclonable functions. And if we have more time, then we can go into the information theoretic part in which I'm working. Yep. So this is the typical IoT structure where there are a lot of smart devices connected to the internet, and each one of those smart devices are point of security threat, which if under wrong hand, it can undermine the whole Internet of Things or the whole internet. There are a lot of security threats that we want to um, overcome. Like the first one is authentication. You want to make sure the device that is connected to your network is actually the authenticated and the correct device. You want to protect your IP. That's another use case. You want to securely store data in your smart devices and all those things, which with the current technology, it's kind of there's a potential threat to the current technology, because most of the time it uses a pre-shared key to authenticate the device, which by the use of physically unclonable function, we want to replace. We don't want to have a digital key that helps you to authenticate the device, but the hardware structure itself. So you cannot just copy paste the digital key into another device and claim that you are the authenticated person, but you need to replicate the hardware which we claim, or it's hypothesized that it is physically unclonable. That means you cannot physically manufacture the same device, and you cannot mathematically clone the structure of the device. Let's see one example how the current system works. For example, if you want to authenticate or if you want to communicate with another device, uh, the device needs to send a stored secret key that is stored in its non-volatile memory, which is again an expensive thing. So it sends back the stored secret key. Then the other device decides if the secret key matches or not. Then based on that, if there is a perfect match, then they communicate. So this is the typical structure in the current model, but as I said, the stored secret key is in digital memory, which can be hacked and copied. So what we propose is physically unclonable functions, which is like your fingerprint. I'm assuming your fingerprint cannot be cloned. Similarly, there is this internal or inherent structure of the device which cannot be cloned because it's inherent to that particular device. And this device is, these inherent features are usually very tiny. So it can be inserted into anything, like, for example, in this case, a banknote, which is very thin. There also you can use the inherent structure of some sort of device to authenticate if it is the correct banknote or not. So it basically works like your biometric or fingerprint. You don't store your biometric in the digital form, but you store biometric in the physical form in your body. So this basically solves a lot of problems that relates to random number generation, cryptographic key generation, secure storage, IP protection. Uh, yep. So these are the protocol, how it can be used into all this scenario, but I won't go into the details of it. I just want to introduce what is a PUF. So here's one particular example that I will give. So right now in the quantum age, we don't have quantum computers at our home. We have quantum computers in some IBM laboratory, which we can access by cloud, and we need to pay for their service. And if we are paying, we want to make sure that if you are paying for the good hardware device, then we actually run our protocol on that device, not on any other device. So in that case, we can use physically unclonable function to actually authenticate that device, that our protocol that we sent to IBM is actually running on that hardware device for which we are paying, but not in some cheap hardware device. So this is a particular use case for PUF. And throughout the years since the introduction of PUF in the year 2000, we have seen a lot of companies have filed patents for PUF, and it has seen we have seen growing interest in the PUF technology because it's alternative to key distribution or storing of key in non-volatile memory. Let's see one particular example of PUF construction. So here it's a capacitor that we built in by the current technology. Suppose we want to build a capacitor of 5 capacitance, but due to hardware variation, it will never be exactly 5. It will be like 5.0001 or 4.9999. So there will be some errors in the manufacturing. What we do in the PUF construction is we put a lot of we align all of these capacitors and profile their variations. Now using some sort of encoder, we generate a secret key out of the it's the profile of the device based on the variation. So this particular part, we generate a secret key from the variations that we got in the manufacturing process. Similarly, we have another example of silicon PUF where we pass current from the circuit. And if the current passes, so both the top layer and the bottom layer are almost identical, but due to inherent variations, we see tiny difference in how the current is received at the other end. So if it passes from the top one first, then we consider it to be 0. And if it passes through the bottom one, we consider it to be 1, or the vice versa. And we also align a lot of these structure to generate a variation profile out of it to uniquely identify the device. Now, why do we call it a function? It's a physical device, but it is called a function because it is modeled as a function. You provide an input, which can be current signal, and you get an output out of it, which is usually binary bits. And in typical PUF term, we call it challenge and response. The input is called challenge and the output is a response. So what we do is after the manufacturing of the device, we collect all the input output behavior. And the next time we want to verify if it is the same device, we provide the challenge or the input. And then we see if it is if the response is same as the one in our table. So this is the typical authentication protocol where during manufacturing, we create the table for the challenge and response. And for authentication, if we want to verify if it is the same PUF, we provide the challenge and we try to match if the response is same as or it's different. So there should be some sort of properties between challenge and response pair that makes PUF usable in cryptographic schemes. Like if you provide same challenge again, then it should give same response again, no matter the environment condition is. And if we apply same challenge to different PUFs, it should give different response. And if you apply 2 different challenge, it should give 2 different response for the same PUF so that it can be uniquely identified. Next, the most common attacking scenario is there's an attacker who taps into the challenge and response that are communicated over the server. And he collects and store all the challenge response that we communicated. And based on the challenge response stored on his database, he tried to predict what will be the response of the next challenge for the PUF. For example, if he knows the challenge response pair for the first challenge, then he tried to predict what will be the response of the second challenge. It is basically based on machine learning attack where they try to find correlation between already existing knowledge. And based on that, they try to predict the outcome of what is not known yet. So this is a very common attack in classical PUFs. Okay, now for quantum PUF, what I will do is I will go through some of the models, how quantum PUF has been proposed so far. So the first and the most common quantum PUF is QR PUF, also called quantum readout PUF. In this case, we assume the challenge or the input state to be a quantum state and the output state is also a quantum state. So what happens is, since the input and output states are quantum states, it is protected by no cloning theorem. So the challenge response profile that the eavesdropper wanted to make in this kind of attack, it's not possible because of no cloning theorem. I have not commented anything about the internal structure because in this kind of PUF, the internal structure can be anything like the classical PUF. So what we do is we have a quantum state, we convert it into the classical input by a decoder or encoder at the end. And then again, we convert back the classical output into a quantum state, then transmit this quantum state using QKD or some other protocol. So the challenge response profile is hidden from any third party. One type of this QR PUF example is this optical PUF, where we pass laser beam from into a 3D. This is a device that actually scatter the laser beam into a speckle pattern. And based on the pattern profile we got, we try to identify that particular device. So basic idea is to encode quantum state in the laser beam and get a different kind of pattern for each input that you provide. The main disadvantage of this is once you provide, like this is highly sensitive, so it is, yeah.
We have one question.
Yeah.
If I may very quickly, just a question about understanding. The first PUF you showed, it converted quantum information into classical information back into quantum information. I would think that you could clone the classical PUF and just reproduce the classical behavior of the function, and you would basically get the same result back.
Yeah, if you can clone the classical PUF, then yes, you can clone the QR PUF. But what we are trying to achieve is, or the authors were trying to achieve is to come up with a protection against this kind of attack where they are not cloning the classical PUF, the device itself, but they are collecting the challenge response, the input output, and then they are trying to predict the behavior of next output.
But couldn't you then just convert the quantum information to classical information again and train
But
based on that?
they don't know what challenge you are sending in the quantum state. They need to measure it because it's a random, like there are multiple challenges available. You are sending randomly out of it. So unless they have the same decoder that you use to convert the challenge, or unless you know the exact state in which your challenges are encoded, I don't think you can decode it with 100% probability. So the main idea is to hide the challenge response behavior by encoding them into the quantum states. But if you can clone the device itself, then there's no security. So it's kind of like based on the assumptions, or yeah, it's based on the assumption that the device itself cannot be cloned because it's inherent feature of the device. So there are, like I said, there were like multiple patents for PUFs, but not all of them were found to be physically unclonable. So the main idea is to hide what is the encoded information in the challenge and output response. And there are like other PUF. In this case, we again assume QPUF to behave as a unitary map that converts the input state into output state. But this is found to be not secure against quantum polynomial type attack. So if you give the PUF to a third party and they analyze the PUF, and based on their analysis, they can come up with a mathematical model of the PUF. So if they have exponential time with the PUF, I mean exponential input output behavior, So they can actually model these kind of puff. That's where Christian and his group come up with non-unitary puff, which was proven to be secure against quantum polynomial type attack, where even after polynomial amount of time, the eavesdropper cannot come up with perfect input-output behavior. Okay, the other kind of puff that was presented is the based on errors. So in each of the IBM devices, there is a different kind of error, like 1 or 2 qubit gate errors. And there is also crosstalk errors, which behaves randomly and unpredictably. So the idea was to distinguish all these devices based on their error profile. What they do is they encode the challenge into some kind of circuit, and they run this circuit on the device, and they try to find out what is the error profile in the circuit. And it is for some type of error, it turns out if we run this circuit again, we get same error profile for the same device. So they use this concept to come up with quantum puff based on error profile, in which they apply some rotation operator and Hadamard gate to get the error profile. But again, this one was shown to be unsecure if we only use one rotation gate. So later on, they implemented or they come up with a new type of circuit which can give better error profile and is claimed to be more secure than a single rotation operator if we combine multiple rotation operators together. The other kind of quantum puff that is proposed is based on quantum tunneling effect. So if we keep on decreasing the size of the device, then quantum confinement will begin to operate, and there the tunneling spectrum is different for each devices. And this copying these particular type of tunneling spectrum is almost impossible because you need to arrange each atom in a particular order to get the same tunneling pattern or spectrum. So based on this tunneling spectrum, they also come up with a new type of quantum puff. Next, again, coming back to QR puff, because QR puff is the most simplest structure, and the latest paper that I have seen is the hybrid puff, where they combine the classical puff, where they give classical inputs, and there is some encoder that outputs the quantum state, for example, BB84 states. And these are protected by, again, no cloning theorem and indistinguishability of these states. And they claim the security of classical puff using this quantum encoding. And they also prove that if they apply some additional cryptographic scheme on top of this, then it can be proven to be secure against quantum polynomial time adversary, where even if you allow the adversary to have access to the device, then also the adversary cannot make a profile of input-output behavior properly. So yeah, these were some examples of quantum puff, just to give you a review of what is going on in the quantum puff. I'll quickly go through the information theoretic model of quantum puff, like how do we consider puff in information theory. So puff in information theory is usually considered as a bipartite source, but if you allow input, it gives some output. We denote with random variable. Then we use encoder to generate a secret key. Then again, if you apply the same input, it gives some output yn. Yn is supposed to be correlated with xn because it's the same input, the output should be same. But puff are very vulnerable to errors or environmental conditions. So if you change the environment condition, there is high probability that there will be some error. So yn, you can consider it to be xn with some error. And then we use decoder to get the estimate of the secret key S. And in order to error correct, we also consider public helper database M, also generated alongside the secret key in order to error correct later, so that S hat and S are almost close to each other. So this is a particular protocol of generating secret key out of PUF. So we combine these two operations together to get something like bipartite source kind of structure. And based on this, we analyze how much secret key we can generate out of the PUF. In quantum PUF, like I said, the output we consider to be quantum states, whether it is hybrid PUF, QR PUF, we don't have any restriction on what kind of internal architecture is inside the PUF, but the output we are assuming it to be quantum by some encoder or inherent quantum. So we first analyze the special case of it, where we don't consider quantum state at both encoding side and decoding side, but quantum states. But while the encoding side we consider it to be classical because it's with the manufacturer when he is encoding in the first terminal. So he don't need to encode it in the quantum state in the first terminal. But later on, when we are actually verifying, we need it to be encoded in the quantum state just to protect it from any third party. This is, again, the information theoretic model where we earlier saw the generation of secret key, but the same secret key can be used to store some secret message, which can be retrieved later, or it can also be used for authentication. For authentication, what we are interested in to have, it's a secret key based authentication. So again, like we saw in the non-volatile case where you need to present a secret key, and if it matches, then we grant access or we say the device is authenticated. For PUF, again, it's the same thing, but we have like two kinds of error: false rejection rate, where the secret key does not match, it may be because of error, and false acceptance rate, where the eavesdropper is able to authenticate itself in a wrong way, or say by providing its own input instead of the actual response of the PUF. This is just one example of information theoretic calculation that we did in our work, bounding the false acceptance rate for the case of quantum PUF. Yeah, again, and we also gave relationship between the false acceptance rate and the secret key you can generate. So if you generate the large amount of secret key, then you can get more security in the authentication. Yep. Thanks.
Questions? Maybe one question.
I have another question of understanding. Quantum PUF could have a classical input. Is that correct?
It's one type of quantum PUF that is proposed.
And then you would deterministically have the same quantum state as an output.
Deterministically in what sense?
Well, I mean, for it to be a function, it needs to give the same output to the same input, right?
Yeah. So if it is the same output, then it will give the same quantum states.
How do you deterministically produce the same quantum state every time? I thought that wasn't really possible.
You just, you don't produce the quantum state, but in the hybrid case, you basically encode the classical output that is generated. So you generate the classical, because it's classical PUF, you also generate the classical output. Then based on some encoder, which say 0, 1, I will consider it to be in the 1 state. If it is 1, 0, this is just one example, we consider it to be plus state.
So you have kind of a quantum output with a very pointy distribution, kind of, because it's like it's encoded, so it's very pointy on one state. It gives you kind of every time the same classical output. If you were collapsing it again.
If the input is same, then it will give the same quantum output.
Thank you.
Yeah, because you don't want different output for the same input the next time in order to verify. That's the main thing. If you are giving same input, it should give the same output.
Okay, then let's thank Nilesh again, and we are looking forward to the talk by Dan Kilper.